finished what we want to talk last time. So let's continue on this single electron transistor, right? Which is important for qubit sensing, particularly for the silicon qubit. So last time we have started from something very basic, right? Just one gate on quantum dot to understand how the charging effect affects the transport, right? What is charging effect again, or Coulomb blockade? Is that because when the capacitor is so small, when you add one more electron to it, the potential increase a lot because, right? And so you would not be able to put in one more electron. But that was just a simple case. Now we look at the single electron transistor. So we already covered this slide in the last lecture. This is a transistor. It has 3 terminals. We can call this source or drain. This is drain, this is source, and this is the gate. And we have this quantum blocking you, right? So we have this quantum dot here. Again, this is a dot, very tiny, because we want to make a very small capacitor. And it is coupled to the source, drain, and gate through 3 capacitors, right? What important is that the gate capacitor is maybe thick enough. The main point is that we do not want to have any charge transport from the dot to the gate. But we allow charge transport between the source and the dot and the source and the drain. Here we just call it left and right. And how can they have this interaction? Because we allow tunneling. Okay, so we design it so that it can have tunneling. Yeah.
So from source drain to the on dot, you have capacitors CL and CR.
Yeah.
So how do you get tunneling current? Because that just means if you have a capacitor, DC current is 0.
No. Capacitor means you have capacitance, but it is thin enough that you can have tunneling.
Oh, if electron.
You don't really put an ideal capacitance, right? It's just some coupling. I don't have the figure here. Maybe later you will see it. It's just like you have a wire and then have a certain distance to the quantum dot. And again, this can be also just a barrier, right? A potential barrier you created by your barrier gate, for example, right? So last time we already said that. Then what is the energy of the electron, right, of this system? It is equal to EC, right, times N minus Q over E. What is N? N is the number of electrons inside this dot, right? And what is EC? EC is the charging energy for this problem. When we had the simple problem, it was just E squared divided by 2C, right? Because the energy of the electron of a capacitor is just equals to half Q squared over V. Q squared over C. Right, so that's why you have this form. Again, this is just a definition because this is a constant that pertains to this system. Okay, now, and then we also define a quantity called Q. Q is just equal to CR, right, capacitance times VR plus CL times VL plus CG times VG. This is something we define, but this is not something called we can say the electro-induced charge in this sense, right? It doesn't have a direct physical meaning, but this determines this Q, right, based on the capacitance and the voltage. And last time I said when in E274, if you have taken it, when we talk about the superconducting qubit, we do have this Q also when we have the source, right? Again, it's just a definition. So the question is that now let's say I have N electron, capital N electron here. How can I change the number? Actually, this is very easy. It's like almost like kindergartner problem, right? You ask, I have a box. How can I change the number of pebble in the box? Right? The kindergartner, you can take one out, then you have one less. You put one in, then we have one more, right? That's it. So you have a chance to go from N to N plus 1. So you can have from the left, FL means from the left, again through tunneling. You can tunnel one electron to here, or from the right, Fr, right? Or you can take it away, change it from capital N to N minus 1 to the left or to the right. Only these 4 possible processes, right? So very simple. Sometimes when we do quantum mechanics, it is just counting the number. Like if you study solid state physics, we talk about the density of state. That chapter we're talking about, the title usually is state counting. Really counts. How do you count it? But then it turned out to be a complicated equation. Yeah. Which one? Just the electron energy of the electron in this system. Yeah. You just think about the system energy due to electron. Okay, so let's look at the process, the energy of this 4 process, right? So we have 4 process. Let me just write it down. And we discussed this earlier. From the left is tunneling from the left electrode to the quantum dot, right? So the energy, we call it delta EFL when you start with N. So what is the energy that you need? Well, it becomes the energy of the system after the tunneling, right? After tunneling, the energy of the system becomes N plus 1, right? We were saying that if you have N electron, this one basically means EL of N. When you have N electron, you have this energy. So if I tunnel 1 electron into here, then I have N plus 1, right? Just by definition. But how much energy do you need? What is the difference? Then I need to compare to what I had earlier. Okay? But at the same time, there's work done by putting this electron, 1 extra electron, through this voltage gate. So you have this one, minus EVL. Okay? So this is the energy difference. If I manage to tunnel 1 electron from the left into the quantum dot, I need to provide this amount of energy. It can positive or negative. Yeah.
What's the voltage on?
It doesn't matter. EVL, because I take away 1 electron, I need to refill it with 1 electron. Then in the whole process, the system will have this change of energy. Yeah, it's not due to potential difference, right? So how about to the left? Can someone tell me? If to the left means I lose 1 electron, right? So to left, how should we do that? After I have 1 electron going to the left, how many is left in the quantum dot? Thank you, N minus 1. So it's going to be EL N minus 1 minus what? The original energy, right? Minus En, but it's to the left, so now it is EVL plus EVL. Okay, so we can follow the same tokens from the right. You tunnel from the right, and the question again is from the right, when I start with N, the change of energy is going to be EL N plus 1 minus EL N, right? And then minus EVR. Okay, because on the right I have the voltage, which is VR, right? Any questions? Yeah. No, we won't go to so deep. I just want to show you how it look like, and then we'll talk about how you do the transport. I'm not doing Hamiltonian. We're doing just to show how we can control single electron. Yeah. So to the right is what? When you tunnel to the right, how many electrons I have now? Thank you. n minus 1, compared to before, which is n. And then because it's tunneled to the electrode, so EVR. Okay, so what is the energy? My question is, then what is the energy, right? I wrote down all this equation, but they always just have plus or minus. So I want to know what is EL n plus minus 1 minus EL n, right? All this n plus 1 minus n or n minus 1 minus n, right? All of this. I just want to know what it looks like. So if I just go into the equation, what is this? It's just EC times n minus Q over E squared, right? So this is equals to, they have the common term, which is EC, and then I have n plus minus 1 minus Q over E, the whole thing, square, and then minus n minus Q over E, the whole thing square, right? So EEL of n plus minus 1 is just EC times n plus minus 1 minus Q over E square, right? ELN is just EC times n minus Q over E square, right? The only difference is one has n plus minus 1, one is just n, right? So if you go through the math, I don't do that, you get that this is 2EC, I hope that I'm right, times plus minus n plus half minus plus Q over E. Okay, so this is the math. It will be interesting just to do a checking, right? So I don't draw any conclusion. I just show you that how to do the calculation. Okay. Now, let's do a checking. What if I have an electron, which is from the left, right? I have a process that is from the left plus to the right. It means that I have an electron go into here and then go into here. How many electrons I have? N, right? So there should be no change in energy in the system. But how much energy do I need to do this whole process? Based on this, delta E is just equal to delta E F L. From the left, I start with N plus delta E to the right, right? But when I do to the right, it is N plus 1, right? Because I had N. You tunnel 1 into here, it becomes N plus 1. And then now I want to remove 1, it is starting from N plus 1. Make sense? Can you follow? Now, if you go through the math, look at this carefully. If this is N, right? Or we even don't need to use this equation. If this is N, then this is this equation, right? Maybe I just write down everything. So what is this? This is equals to, well, EL N plus 1 minus EL N minus EVL. That is the first term. Correct? I just copy from here. How about this term, PR? What should I put now? He said ELN, YN, not N minus 1. Because we start with N plus 1. Very good, right? So this is N. Minus EL, this time we have N plus 1. And then plus EVR. And you see clearly, N plus 1 got cancelled, N got cancelled, right? So the whole thing is equals to negative E VL minus VR. So isn't that this is the total energy I need to move one electron from across this potential difference? Maybe the positive minus need to treat a little bit, right? So this does represent, so here go back to why we have this, because this is energy you need to do, you need to provide in order to cause this change. Okay, this is just a check, right? Just for better understanding. Okay, so why do we want to do this? This is what we want to say, right? So assume we are at low temperature. What does it mean? It means KT over Q is very small. 10 millikelvin, for example, right? Your silicon, your qubit at that temperature. So because of this, you can only have tunneling for transport. Right? But when can you have a tunneling? It is only possible if the delta E is smaller than 0. Right? You only can change the state if you attain a lower state. Okay? So if I want to go into the Coulomb blockade regime, right? If I want to block all processes, what does it mean? No electron can go in and out of the dot. Make sense? I want to block all of them, right? Then what do I need? I need delta E TR, delta E TL, delta E, or else TL, delta E, not TL, right? FL. FR, maybe I start with FR. From right and delta E to right to be what? To be larger than 0. Right? So that if they want to have this process happen, they need to gain energy. But it does not. And in that case, then we have no tunneling. This is the Coulomb blockade regime. This is the first thing. Make sense?
So
but this, yeah.
So if any of the
Huh? Yeah. If it's greater than 0, it means that if I put an electron to here, then the energy rise, right? So I won't be able to tunnel into there. That is what it is saying here. So if I want to go in, no, I cannot. Because my destination has a higher energy than me. Make sense? That is Coulomb blockade, right? That's fine. When I block it, that is fine. But how about single electron transport? How can we ensure that only one electron is transported at a time? This is very important, right? Because for some experiment, we want to have one electron. And how do we do that? First, I redraw, this is regime 1, right? This is the Coulomb blockade regime. Let's look at the well again. This is the dot, right? In the middle is the dot. And now this is the energy landscape. So here say that I start with n. I can become n minus 1, or I can become n plus 1. If you want to be n plus 1, then because of the charging effect, your energy becomes this. If you want to put an electron here, you need to bring up the energy to this level. If you lose one electron, then your energy level will go down. Again, this is just because of this one. Look at this equation. Because energy proportional to n offset something square, right? So if I have more electron, my energy goes up. If I have less electron, it goes down. Now I start with N, yeah. Barrier.
Yes, that
This is for tunneling. This is barrier. So we all talk about tunneling. So barrier doesn't matter. You don't have to because you're not relying on fermionic emission. You're relying on tunneling. Of course, if you lower it, tunneling will be easier, right? But now we just assume they have the same amount of barrier. Okay? Now, this is my Fermi level on the left. If it is at this level, it means my electron at most only have this energy. If I want to tunnel one electron to here, after I tunnel it, because of this charging effect, I need to, the electron can, it only can come to this state.
But wouldn't it jump to the next, to the right, then immediately because that's lower?
Then again, I think so he's saying that can you just go all the way? Yeah, then this is a more low probability process, right? Because equivalency, you are doing two tunneling at one time. You need to stay here. This is also a barrier.
Yeah, but this is not fermionic, if it's tunneling.
Yeah.
It was harder to tunnel from the left to the quantum dot.
It's not harder, no. It is that from here to here, you just cannot go there because you don't have the energy. Let's say you have 1 eV, this is 1.1 eV. If you don't borrow energy, you cannot become 1.1 eV. You see what I mean? You only have this energy, just conservation of energy. You start with 1 eV. You cannot become 1.1 eV if you don't borrow energy. No, this is, and doesn't matter, right? The point is when you go in, the system need to be this energy. It's just like you join a society, right? Yes, looks like when before you join, they can accept it. But once you join them, this is a very bad, difficult to do an analogy. You see what I mean? When the electron goes into here, your electron can don't even think about what is it. Think about you add an energy to an atom. If your hydrogen already have 2 electrons, you add 1 more electron, you need to go to 2s location. Yeah, you cannot say that, no, your 2s is lower than me. But no, you can only go to your 1s is lower than me. My energy is between 1s and 2s. But you cannot replace the 1s, right? You need to go to 2s, so you cannot go in. Make sense? Right? So you cannot go in. And you say that, can it go here and immediately? Then it's like something called virtual state. It's possible, but the chance is very small. First, you need to stay here, and then you need to tunnel again. You just, if you from classical point of view, classical but quantum but classical point of view, you even cannot come here at the first place, right? Then how can you come here? Okay, so this is a Coulomb blockade regime. Similarly, can this electron from here go to here? Maybe N has a higher energy, but once you this one, I cannot say that. We think it in another way. For example, can this one go in?
Yes.
But no, right? Because again, when you go in, it becomes plus. So you cannot go to this level, right? It was N, right? How can I go into here? This is just the same. Actually, I should not point at this. This doesn't mean that it comes from here to here. It's just talking about going from here to here. It's the same as going from here to here. You cannot. Okay, so this is a Coulomb blockade regime. Okay, so now let's look at a regime that we can have single electron transport. If we look at this, right, look at B. First of all, do we have from left? This is from left. Is it possible? Of course, right? Because I do have electron that has a higher energy than +1 state. Yeah. N, as I say you right, it is N, and then it become N+1 or N-1. You start with N. If you tunnel in, it becomes N+1. If you remove it, it becomes N-1. Yeah. But again, it doesn't matter, right? I just told you about the hydrogen example. It doesn't matter where's the energy of N. It only matters what happened if you successfully tunnel. Make sense? Again, this is quantum mechanics. Think about the hydrogen example I gave you. This is same. Hydrogen is your so-called orbital is just discrete energy level. This is discrete energy level. A quantum well is a hydrogen is just a quantum well, but in spherical coordinate. Right? Okay. So now you have, how about in this state? Now this one is higher than this one. So is it possible to have FL from left? Yeah, of course, right? So we can have delta E FL N is smaller than 0. So this is okay, right? Because we can, I mean, it has enough energy. It doesn't need to come from top. It can just come from anything below the Fermi level. Now, then the point is this. After I transport one electron, can I add one more electron? You need to get to n plus 2. Very good. But n plus 2, we will make it such that it's higher than this guy. Right? So here is, maybe this is plus 2. Right? So you cannot have the second one. Cannot have the second one. No, because we talk about low temperature. So it's not about probability. You just cannot get there. Right? If you have that probability, just because you have thermal noise, which we don't want. Right? So you can only have one at a time. Right? So here I want to say that delta E F L n plus 1 is larger than 0, so not okay. It's not good. Right? So only one electron. Make sense? Now, then if that is the case, right, is it possible that when I have plus 1, when I plus 1, can I have electron going back to here? No, right? Because the energy level is higher than my plus 1. But I can have electron going to here, right? So I can have delta, maybe I make it blue, delta E to right n plus 1 is smaller than 0. This is okay. Make sense? So you see that when the electron go from left to right, every time only one electron can get in and only one electron can get out. You might say, can I have 2 electrons get out? No, once you have this electron gone, then I will also, this is not clear. We also need to have the n at a level lower than this. You cannot go to here. Okay, so that is how you arrange it so that you can have only one electron at a time. So that is the single electron regime. Is what?
Is this practical because T cannot be 0?
But can be very low. So he's saying that is still practical. Of course, people already show in experiment. How do you remember last time we talked about the charging capacitance, right? Recall? The charging capacitance, the charging energy is in the order of Q over C squared. Q squared over C. You make C very small, or T very small, then you can have this single electron effect. Because when C is small, the separation of this level are large. then I really can do one by one. Or make T very small, even your separation is not large, I do not have this Fermi tail that have this fermionic emission, right? If it is absolute zero, only this electron, I only have electron up to here, right? If it is 300 degrees, you might have some tail. And also in the tunneling process, it can be inelastic. You borrow the energy from photon, then you can climb to a higher level in the tunneling process. So that's why it's related to cryogenic, right? Yeah. Of course, tunneling is not fermionic. Fermionic means what? Means you go over the barrier. Yeah. No, you don't have. No, fermionic is not tunneling. Fermionic means you have enough energy to overcome the barrier classically. Tunneling is not fermionic. Tunneling means that your energy is lower than the barrier energy. Classically, it should not happen, but quantum mechanically, it happens. Yeah.
It's almost like, it seems to me by default, you're designing the operation to be fermionic and not the way you're describing.
No, you don't want to do fermionic because you don't have control on the electron. Once it's fermionic, you don't know how many electron goes in. Right? You need to count one by one.
But then I see you're almost implying that you don't need a barrier.
Again, do not confuse this with the spin qubit plunger gate or barrier gate. That is a way for you to transfer one electron to one well to another well. But here we're talking about single electron transistor, that we have a barrier there. We don't have an extra gate to control this barrier. We have a very tiny capacitance, so we have a very big discretization in the energy. And through tunneling, we can control one by one. This is nothing to do with the spin qubit, right? I think you're thinking about this is the plunger gates, these are the barrier gates, but that's not the case.
So the barrier is like center, then
Yeah, we are not moving the barrier usually, right? You may change the energy of the gates here, the voltage of the gates, and then the voltage of the left and right. So you only have 3 gates usually for single electron.
So you're like,
Yeah. Right. Just like here. Just like here. Okay, so then I want to talk about this Coulomb diamond, which you need to do it in your assignment, right? So we are going to simplify the process. I gave this to you earlier in the previous slide, right? I did not derive it, but I just copy it. But what is that about? Now, one very important thing to simplify the math and also for the experiment, usually people just make VL equals to V over 2 and VR equals to negative V over 2. Okay, so just make it symmetric. This is the thing, right? So EV is the total energy, right, from left to right. This is one simplification. Not simplification, I'll just make it simple, right? Now, again, we have this Q, which is CR, VR, plus CL, VL, plus CG, VG. Okay, this is the induced charge, right? So what is the Coulomb diamond? So these are the Coulomb diamond. Okay, so this Coulomb diamond, maybe I don't write it, in a single electron transistor. So if you are in this regime, if you have the charge in this regime, and these are the n, this is n, n equal to 2, n equal to 1, then it is the blockade regime, right? So this is Coulomb blockade. So if you operate in this regime, so no charge transport. In this gray regime, then you have single electron transport, right? Based on what we discussed earlier, you see that we need to make the condition it is very delicate. We need to make it right so that we have a single electron transport only under certain voltage and also under certain charge, okay? Exactly. Yeah. Yeah. So Q is controlled by the gate. You're right. And here we already fix it for each of these EV, right? For each V, we fix it. So for each V, and then when you sweep the gate, then you will see that I will need to, for example, the V need to go to this level, and then I will be able to change the number of charge from 1 to 2 or 2 to 1 when I'm sweeping. Yeah.
What's the difference between this one and the parabolic?
The last time the parabolic port is for a two-terminal device, right? And that two-terminal device is telling us it's gate voltage here again because it's the induced charge, right? At each gate voltage, it will determine how many electron can exist in the quantum dot, right? The parabolic plot, each plot, right? If you guys forgot what he's talking about, I'm going to erase it. But last time we have something like this, and then we have the energy, and then we have this curve. Remember? And then you just for a certain gate voltage, then you find this is the lowest energy, and this is correspond to n equal 1. Then it means at this gate voltage, you will have 1 electron in the quantum dot. Because 0 electron will give you a higher energy compared to other electron. Right? So that is for another problem that we had a gate and then coupled to this is the quantum dot, and then do we have a resource? I think so, right? And this is N, just a two-terminal device from last time. Okay, so you can take a look. But anyway, don't get confused. Now we have 3 terminals, so this is the energy landscape. So that's how people study their quantum dot. They will sweep the gate voltage at different source drain bias, and then if you have a transition, you will see the current suddenly go up because the electron can tunnel into it. Then you will have this edge mark when you have this transition. Then they can see this diamond. So here I want to just go through some math because I want you to try it in your assignment, right? So let's start with n equal to 0. Okay, so assume I don't have any charge inside. Then what is delta EFL when n equal to 0? So remember this equation I derived? It is equal to this minus this, right? Which then it becomes this, right? And now I wrote it here. This is the difference, right? So you plug in n equals 0, it is equals to 2, because it's 0, right? 1 over half. Should it be plus or minus when it is from left? From left means, do you get more electron? Right? So it should be n plus 1, right? So n plus 1, it turned out to be minus, okay? So it is 1/2 minus Q over E, EC. Let me check if I'm correct. Q is the charge that, Q again is the induced charge, right? Of this guy, right? And E is the the elementary charge. This one, if I want it, and of course I need to also add this EV over 2, right? Because remember this one is minus EVL, right? But now VL is equals to V over 2. So that's why I need to minus EV over 2, right? So in order for this one to have, so maybe I should be more clear, right? I find the diamond. When I say find the diamond, I means that I don't want, the diamond means it's Coulomb blockade. It means this needs to be larger than 0. Let's pause a little bit because the rest is just the same. Do you understand what I'm doing here? We start saying I have zero electron in the quantum dot. And now I want to know what is the area that will block me from having the tunneling. We have Coulomb blockade. Let me remind you again. This Q, right, is related to VG, the gate voltage. And this is just VL minus VR. The difference of the left and the right electrode potential. And now I want to know in which regime I cannot transport any electron. So I start with N equals 0. And then I try to find out what it is. But it means that to have Coulomb blockade, I need to have the change of energy larger than 0. It means at low temperature, then it means I cannot do it because I cannot get energy from elsewhere. Then how can I do something to increase the energy? Okay? So I have this one. Yeah.
So if you know, so I print something.
No, I only doing first equation. Let's do it one step by step. You will see what I'm doing later. Now I'm only saying that what is the energy if you want to get one electron from the left. This is the energy you need to get one electron from the left based on our derivation earlier. And this one I gave to you, right? From left is n plus 1. So this is minus, right? Because top is minus. Top is plus, turn out to be minus here, right? So that's why I plug in n equal to 0. Then I have 2/2 minus Q over E times EC. You need to do this in your assignment. So make sure that you understand, right? Now, then Coulomb blockade means everything. I also need to make sure tunnel to the left when n equal to 0. Now this n is just an extra electron, right? So you can have negative 1 electron. That is fine, right? So what would this be? Tunnel to the left. Tunnel to the left means that I have n minus 1, right? After I tunnel to the left. So I need to use negative, and here it will becomes 1/2 plus Q over E. EC minus, but this is plus because it's to the left. It's tunneling out over 2. Again, this needs to be larger than 0. Make sense? Any questions? So if no question, how about any volunteer? Another process I need to block it is from the right. Start with 0, right? What should be the equation from the right? We will use this one, right? First of all, this is 2, n is 0, half, and then minus Q over E because we get an electron into the extra electron into the well, right? So this will be minus Q over E, EC. And then you need to look back because it's tunnel in, but it's from the right, so it is This one, that is because our right has a potential of negative V over 2, right? So minus negative V over 2 becomes plus. Okay. Okay. One more. Anyone? Not you. Anyone else want to help me? To the right. So get an electron from the quantum dot to the right. How would the energy change? 2 times 1/2 plus. Why it is plus? You take it out, so this is n minus 1, right? So it's lower, right? So it is plus, correspond to plus. Very good. And then how about the next term? What is that? Minus, yeah, it need to be opposite, right? Okay. So if you fulfill this condition, then you are in the Coulomb blockade regime, right?
So all of them.
All of this condition. So let's take a look. Let me call this 1, this is 2, this is 3, this is 4. So for 1, what is the condition? It says that EV over 2 need to be less than 1 over 2 minus Q over EC. Right, correct? This one needs to be larger than 1. So then this one needs to be smaller than this guy, right? Now, if I look at here, this is just a XY plot. This is EV. So this is Y. And then this is Q, which is related to VG. So we are saying Y less than, or think about equals to mx plus c, right? So what is the slope of this? So slope will be 2 times Q over E times E, right? Oh, sorry, you're right. And I also want to put this 2 to here. The slope will be 4 times EC, but negative. Then what does it mean? It should be something like this, right? Because this one has a negative slope, negative 4 EC slope, right? And then what is the y-intercept? It is going to be when Q equal to 0, this is equal to 2 C, right? When you intercept it. Because when this is equal to 0, then this is just 2 times 2 divided by 2 EC. But smaller, what does it mean? Smaller, it means in this direction. This is smaller. What we are plotting is y equal to mx plus c. This region is y smaller than mx plus c. Make sense? So we repeat this for another curve, 2. What does 2 say? It says EV, I'm going to multiply to 2 to the other side, needs to be larger than 4, 1 over 2 plus QEV times EC. Right? The slope is still 4 EC, but this time is positive. And it intercepts at, again, 2 EC. Intercept at 2 EC, but then it's positive. It must be this curve. This is 2. No, I think I'm wrong. What did I say wrong? This is not larger. This is larger, but I forgot to put negative here. EV larger than 0, so EV need to be larger than negative of this term, right? This one goes to here, becomes negative, right? So I'm wrong, so negative. So this again is a negative slope, like this one. However, it intercepts at negative 2 EC. right? Again, I'm plotting y equal to mx, but now it's y larger than to mx, right? So this direction is 2. It means all area above this curve satisfy this equation. All area below this curve satisfy this equation. But I need to satisfy all of them at the same time, right? So only this area satisfy both of this equation. So homework, I will stop here, go back, finish 3 and 4, and I can give you a hint. You will get this. This is 3, and this one, this is 4. So in order to satisfy this 4 inequality, only this diamond satisfy all of them. That's why if you have a gate bias within this regime, and you have the source string bias within this regime, you would have a Coulomb blockade. So in this regime, you won't be able to have any transport of electron. Now, so go back to, if you took 274, right? We use single electron transistor to sense a charge. When you have a charge, it changes the potential of the quantum dot. Then you will be able to transport the electron, and then you can measure a current. But if you don't have charge, you put it in this regime. Now in this regime, then you won't be able to transport. So once you have a charge next to your single electron transistor, the whole thing shifts because you have a big capacitive coupling. Then you will be able to transport. For example, maybe you can bias it here. When there's no charge, then no current in the single electron. When there's a charge, I'm talking about a charge outside of the single electron transistor. And you have a charge, then you have current. Then as a result, you will feel the current. Then you know that there's a charge or not. And there's something called spin to charge conversion that convert the spin information into charge so that you know that whether your qubit is spin up or spin down. So I won't go into detail, but the summary here is this. You will see this often. Maybe you feel it is useless to you. In some sense, if maybe, I don't know. But if you if you have an application of designing a chip for quantum sensing, right? No need quantum computer, just sensing. This is very often, right? You will run into this diamond, and at that time, just refer to this slide again to help you brush up. Yeah. Okay. Question?
Yeah, but this model is not physical.
What do you mean by not physical?
Well, generally, you have to go to test. So, single electron transistor with the ion, some arrangement, some materials. It seems like this one's so little so that it's very under black box.
Yeah, it is a simplified model, but it is good enough to explain what you will observe experimentally, the diamonds, right? But it's just that your single electron. First of all, it doesn't need to be, here we never talk about the shape of your quantum dot. All we say is just you have a dot with a certain capacitance, right? So what it cannot account for is, for example, the parasitic leakage, right? For example, it can lead to the gate, so there is a problem. Another is, for example, photon can assist the tunneling. Then you will leave this single electron regime easily. Yeah, and tutor, because that is a good point. He said this diamond is going to tilt in the real case because these capacitors are not fully decoupled, where the voltage here can affect the shape of the potential in the well, right? So this is only for ideal case. So indeed, right? So what we're trying to say is that the effects of the gate charge depends on the EV also. So this is just an ideal case. You're right, yeah. But this is the fundamental model. Okay, and I know some people try to do something so that make it not tilted. Yeah. Just fundamental. I'm not teaching anything advanced. I don't know that well, neither. Okay, so this is cover. This is a summary.